Okay, representing aqueous reactions. So there are different ways to represent reactions. The molecular equation is what we typically think of as a chemical equation. It's going to show all of the reactants and products as neutral molecules. So here we have potassium hydroxide reacting with magnesium nitrate to form potassium nitrate and magnesium hydroxide. So this is representing the compounds as if they existed as molecules. But we know that soluble ionic compounds dissociate in water. And so this potassium hydroxide is not present as molecules, it's present as separate ions in solution. So a complete ionic equation shows all of the species as they're actually present. So it'll show potassium ion and hydroxide ion and magnesium ion, etc. Magnesium hydroxide is a solid, and that's how it actually is, and so that is shown as an intact compound. The net ionic equation only shows the species that actually change, so only the things involved in the chemical reaction. So we talked about this as like, two people, guy and a girl going to a party, guy and a girl going to a party, and this guy and this girl, potassium and nitrate, do not become involved with anyone at this party. They are just still mingling. They're the same as they were before, individual ions. And so those did not actually change in the chemical reaction. And so we're not going to show those in a net ionic equation. We call those spectators. They're just watching. It's the magnesium and the hydroxide that had the chemical reaction, and now they're together. So the net ionic equation is a little bit like your net paycheck, right? There's your gross paycheck and your net paycheck, and the net paycheck's always smaller, right? That's the stuff you actually get to take home after they take out the taxes and all the other stuff, right? So it's kind of the bottom line. So to write a complete ionic equation, we're going to write any aqueous ionic compounds as ions, and these would include all of the strong electrolytes. Soluble salts. Salt is just another word for ionic compound. So soluble ionic compounds, strong acids and strong bases. Those are things that dissociate completely or ionize completely. Anything that's shown as a solid, a liquid, or a gas, you don't change it. You leave it as it is. Those include insoluble substances. So like the magnesium hydroxide that was insoluble, you're going to write that as a formula unit. A weak electrolyte or a non-electrolyte. Non-electrolytes don't ionize at all. Weak electrolytes only ionize a little bit. So we're going to write the major way that it is in solution. So for weak electrolytes, it's mostly in the molecular form. Weak acids are weak electrolytes, and so they're also written in molecular form. So here's an example of a molecular equation. So lead nitrate, potassium chloride, making lead chloride solid, and potassium nitrate. The complete ionic equation, we're going to look at this one and we're going to see it's aqueous. This is an ionic compound, and we're going to separate it into the ions. In one formula unit of PbNO32, we have one Pb2 plus ion and two nitrate ions. And so when we take this apart, we get two nitrate ions. It's a little bit like a bicycle. If the lead is the seat and the nitrates are the wheels, you take the bicycle apart, you have one seat and two wheels. Okay, so you show the individual parts. If we have two KCl, then we have two potassium ions and two chloride ions. In the products, this one is a solid. If the state symbol is S, G, or L, you just leave it alone. You just copy it down. So we're not going to do anything to that one. This one's also aqueous, so we're going to separate it into its ions. In two of these units, there are two potassium ions and two nitrate ions. Does anybody have any questions? So in that complete ionic equation, some of those ions we refer to as spectators. So here's the same equation we were looking at in the previous slide. Here in the reactants we have two nitrate ions, and in the products we have two nitrate ions. We have 2 potassium ions in the reactants and 2 potassium ions in the product. Nitrate and potassium came to this party just kind of hanging out, and they left the same way. Nothing really happened to them. They're just hanging out in solution. So those are spectators. It's like going to a boxing match. All these people standing around watching, and when you leave, you're not black and blue, right? Because you didn't do anything. You watched. It's just the guys in the ring that get all beat up. So it's the lead ion and the chloride ions that got into a reaction, and so they are together. Those are the things that changed. Everything else is just watching. So we don't include the spectator ions in the net ionic equations, so we can just kind of cross them off. So there's 2 nitrates on each side and 2 potassiums on each side. The net ionic equation, we just write down what's left. Any questions? Let's do an example. Consider the following reaction occurring in aqueous solution. Write the complete ionic and net ionic equations for this reaction. So we're going to look at this first thing here. It's aqueous. Now most aqueous things we're going to split into ions, but that's an acid, right? Is it a strong acid or a weak acid? It's a strong acid. And see, this is where I can't remember. Did we talk about which ones are the strong acids? I don't think we did. Yeah, it's kind of a flaw in the book. So there are 6 strong acids. Those are the 6 strong acids. And what you do is you memorize those, and then any other acid is weak. So these first 3, HCl, HBr, HI, those are all the halogens. They're kind of in a family there. And then these guys, just nitric acid, perchloric acid, and sulfuric acid. Those are strong acids. They'll dissociate completely. So this is a strong acid, so we are going to write it as separate ions. So if we have 2 molecules of HI, we're going to have 2 hydrogen ions, and we're going to have 2 iodide ions. Does that make sense? Then we have barium hydroxide, and we're told that this is aqueous. This is not an acid, so we will separate it into ions for sure. The only ones that might not separate with an aqueous state symbol would be the weak acids. Any acid that's not one of those is a weak acid. So barium hydroxide will be separated. So this is where we need to understand charges on ions and things, because we have to separate this into its individual ions. So there's a barium ion and 2 hydroxide ions. And you do need to indicate the charges. So barium ion is 2+, and then I'm going to get 2 hydroxide ions, and those are a -1 charge. And then I've come to my arrow. Over here, 2H2O, liquid. If it says liquid, L, we don't separate it into ions. So we're just going to copy that one down. 2H2O, liquid. And then the last one is an ionic compound, and it's aqueous, so we're going to separate that into ions. Ba2+, aqueous, and 2 I-. This I2 is not iodine, the element. This is 2 iodide ions. And so we're not going to write it as I2, it's 2 iodide ions. So there's our complete ionic equation, showing all of the ions. Any questions? Once you get that, the net ionic equation is fairly simple. What we're going to do is we're going to look at our complete ionic equation. We're going to see, well, are there any species that are the same on both sides? So what do you see that's the same on both sides? 2 iodide ions and the barium. So there's 2 iodide ions on each side, and there's a barium on each side. It's not changed. So we're not going to include that when we write it in, because this reaction would happen in the same way if there was another cation there. So hydroxide came with barium, and they're friends, but they're not crazy about each other. If hydroxide had come with sodium, she still would have ended up in a relationship with the hydrogen ion, because the barium ion had nothing to do with it. It was a spectator ion. So we cross off the spectators, and then we just copy down what's left. So 2H plus aqueous plus 2 hydroxide aqueous. And that gives us 2 water liquid. Now, what's a little odd about that balanced chemical equation? The coefficients. Could we simplify those coefficients? Could we make those lower? Yeah, it's 2, 2, and 2. We'd like to have the lowest possible whole number coefficients. So this should be 1, 1, and 1, right? So we would want to get rid of those. Any questions?